Hi, and welcome to Chapter 1, Video 2. This is pages 23 through 51 in the text. We will look at having popper O2 during this recording. So first we're going to look at section 1.7. This is geometric sequences, which is a new kind of sequence. We looked at arithmetic sequences. Arithmetic sequences have a common difference, d. The nth term has the explicit formula a sub n equals the first term a plus n minus 1d. There's another whole class of sequences whose terms come from multiplying a constant r rather than adding a constant d. You multiply the constant r times the preceding term to get the next term. These sequences are called geometric sequences. You start with a term, and then you multiply by r, and then you multiply by r again, r squared times the first term, r cubed times the first cube, and the nth term equals r to the n minus 1 times a sub 1. This is the way you create the sequence. Now let's look at some preliminary information and an application of this idea. First, preliminary, we need some set theory conventions. There is a set called the empty set. It is set braces with nothing in between, which causes some problems sometimes. So we usually use the symbol, a big circle with a slash through it. I write it like this, rather than the empty set. By convention, the empty set is a subset of every set. Also, the whole set itself is a subset of itself. So there's two subsets right away. So if we have the set A equals 1, 2, a set with two elements, we have both A, the set itself, and the empty set as subsets, plus the set containing 1 and the set containing 2. These are proper subsets. And there are a total of 4 subsets to this set with two elements. On page 23 in the text, the author shows that a set with 3 elements has 8 subsets, and a set with 4 elements has 16 subsets. Let's go back. Let's make a chart of this. The empty set, a set with no elements, has one subset, itself. A set with one element has itself and the empty set, 2 subsets. A set with 2 elements, we just did that above, it has 4 subsets, and note that 4 is 2 squared. And a set with 3 elements has 8 subsets, 2 cubed. And a set with 4 has 16 subsets, 2 to the 4. You see that we are moving up in powers of 2. The next table entry would be 232, 2 to the 5th, and so on. The number of subsets that a set has is an example of a geometric sequence with a multiplier of 2. This multiplier r is called the common ratio. Now, the common ratio is found by dividing consecutive terms, side-by-side terms. If you divide the 4th term by the 3rd term, for example, their ratio is 2. That would be the 4th term is 16, and the 3rd term is 8. 16 divided by 8 is 2. This is the quick and easy way to find their common ratio. In functional terms, this is a sub n equals f of n which is 2 to the n with a domain of the whole numbers. Now let's remember that the whole numbers are 0, 1, 2, 3, and so on. An infinite set. In the book, the illustration for this sequence is forming groups, also known as subsets of people, from a finite set of people. You will note that the formula in the book is 2 to the n as well. In general, we won't be starting with 1 equals 2 to the 0 as our first term. We'll start with some other number and multiply r to the 0 and r to the 1, all the way up to r to the n minus 1 times a to the n. See the classroom discussion at the end there for starting with a number different from 1. Let's look at some problems. On page 26, there's a problem with a peasant being given a reward by the king. The peasant asks for a doubling of rubas, you might think of them as pennies, on the squares of a chessboard. So on square 1 you have 1 ruba, and double that is 2, and double that is 2 squared is 4, and double that is 2 cubed is 8. And we've seen this before. This is a sub n equals f of n equals 2 to the n, where n is a whole number. Now let's look at the graph of this. If you graph it, you'll see that you're all in quadrant 1, and you're following an exponential pattern, but it's in dots. 0, 1, 1, 2, 2, 4, 3, 8. See, this is 2 to the n, where n is a whole number. And where you've probably seen this before is over here. Here's the graph of y equals 2 to the x, where x is a real number. So we're using the whole number line instead of just 0, 1, 2, 3, and discrete points like that. Now, by the time the peasant gets to square 10, the peasant has 1,000 rubas, and 10 more squares later, the peasant has over 1 million. As you can see, this is running into some money, and this is characteristic of exponential growth. It gets big fast. So let's look at Popper 2, question 1. If I give you this geometric sequence, here it is, 2, 6, 8, 54, 162, and so on. What is the common ratio? Here are your answer choices. Be sure to pause the video if you need to. Now let's look for some enrichment work, sequences that are not in the book. Here's one. 1, 1/2, 1/4, 1/8. This sequence does start with a 1. What is the common ratio? Well, let's divide sequential terms. This will be 1/8 divided by 1/4 equals 1 over 8 times the reciprocal, 4 over 1, equals 1/2. So this is 1 times 1/2 to the 0 equals 1, and then it's 1 times 1/2 to the 1, which is 1/2, and then it's 1 times 1/2 squared is 1/8, and you'll notice that, see, this is a sub 0, a sub 1, a sub 2, and there's my power right there. So this is my R, and this is my A. Now let's look at one that's a little bit trickier. You'll see these from time to time though. Look at this. 10 minus 100, 1,000 minus 10,000. What's going on with that alternating negative sign? That's very unusual. What's going on with that? So we'll look at sequential terms. Minus 100 divided by 10 is negative 10. 1,000 divided by negative 100 equals negative 10. Negative 10,000 divided by 1,000 equals negative 10. Let's look at this. So we want to say R equals negative 10. So here is 10. Now notice I'm being very careful with my parentheses. 10 times 1. Okay. And here is 10 times negative 10 to the 1 equals negative 100. And here is 10 times negative 10 squared, which is 10 times 100, which is positive 1,000. Wow, look at that. It's making the sequence, and because R is negative, every time you hit an even exponent, you're going to get a positive number. And that's exactly what's going on. 0, negative, positive, negative. So the second term there, the third term there, is negative 10 squared. So that's going to be our positive number. So having a negative R means that I'm going to get alternating minus signs. Now back to the book. On page 25, the author works with finding the sum of a finite geometric sequence. This means it ends. It stops. Look here. We want the sum of a finite geometric sequence. So it has some n terms and then it stops. So here's my sum. I'm going to call it S sub n for sum, and I'm going to add up the terms. A is the first term, AR is the second term, AR squared is the third term, adding them all up, see these plus signs? Plus AR to the n minus 1, the nth term, and then we stop because it's a finite sequence. So here's what I'm going to call my first equation, because we're going to do some algebra with this. S is for sum, and it stops. That's exactly right. It's not plus dot dot dot. Let's back up for a minute and review multiplication of exponents. If I have x squared times x to the third, you know I've got x to the fifth. If you have the same base and you're multiplying, you add those exponents. Let's look at our application here. If I'm here and I've got r to the n minus 1 and I multiply it times r, that's r to the n minus 1 times r to the 1 equals r to the, add the exponents, n minus 1 plus 1, r to the n. Now, so we're going to use that fact. I'm going to take my first equation, S sub n equals A plus AR dot 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 plus AR to the n minus 1, and I'm going to multiply both sides by R. So here I've got it written out, R times S sub n, and R times all the added terms up to n minus 1. And the next thing I'm going to do is I'm going to distribute the R. That's going to be R times A, R times AR, AR squared, R times everybody. Now notice here it's R times AR to the n minus 1, and it's no surprise that it's AR to the n. R times A gives me AR. R times AR gives me AR squared, all the way up to A to the n. Now we're going to subtract the first equation from our new equation. Here, I've got it written here. I'm going to say, here's my new equation, R times S sub n, and I'm going to subtract both sides. And remember, that's going to be a distribution. All of these are going to be subtract. And let's notice, AR minus AR is 0. AR squared minus AR squared is 0. AR cubed minus AR cubed is 0. And in here, there's AR to the n minus 1. And so that subtracts this. And what I'm left with on the right is an A, which is not subtracted, and an AR to the n, which is not subtracted. So let's put this together. On the left, I have RS to the n minus S to the n. Here it is. And I can factor out S to the n. That's S to the n times R minus 1. And on the right, I've got A plus, no, I've got a minus A. A is subtracted, plus AR to the n. And I'm going to write this one first. AR to the n minus A, and then I'm going to factor out the A, equals A times R to the n minus 1. Let's look at this. Picking out the two factored sides, this is Sn times R minus 1 equals A times Rn minus 1. Now I'm going to divide both sides by R minus 1. Here we go. Sn equals A over Rn minus 1 divided by R minus 1. This is a formula for adding them up that works whenever, now be careful, whenever R is not 1. You can't use it on those sequences where we started out with 1 like we did at the beginning here. You have to work it only with things that don't start with 1. Let's look at an application or a practice of this. Here is a finite geometric sequence. A is 2 and R is 3, so R is not 1. So if I put this together, A is my first term, that's 2, and my second term is 2 times 3, and then 2 times 9, and then 2 times 3 cubed is 54, and the next term will be times 3, and then 2 times 3 to the n minus 1. Well, this is getting pretty big pretty fast. 2 times 3 to the 4th is right here, 162. So now, what is S sub 9? If we ran it all the way out, 9 terms, what is the sum of the first 9 sequence elements? So my last one, C, would be 2 times 3 to the n minus 1, 3 to the 8th. And then I would stop, and I want to add them all up. So I'm going to add 2 plus 6 plus 18 dot 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 plus 2 times 3 to the 8th, which is a really big number, Well, I'm really not going to add them. I'm going to say S sub 9 equals A times r to the 9 minus 1 over r to the r minus 1. So S sub 9 equals 2 times 3 to the 9 minus 1 divided by 3 minus 1, which is 2. And these 2's will cancel. So all I'm left with is 3 to the 9 minus 1. And of course, I grab my calculator and I work that out. I use the y to the x key for 3 to the 9. Whoops, that would be x. Y to the x key. And it's pretty quick. Okay, now for the discussion board. All right, discussion board. Video 2, discussion board question 01. That's how to label it. Discuss the exponents in the classroom problem on page 26. What is going on as the author moves from one equality to another? If you end up with PDFs you want me to post on my website with this one, just send them right along and I'll put them up and people can look at them. So that's our discussion board question for this section of the notes. All right, let's have Popper to question 2. Here we go. Here's a big hint. Let's remember S sub n equals A to the r sub n minus 1 divided by r minus 1. And let's find out if A equals 3 and r equals 4, so we've got a geometric sequence. What is S sub 3? Here are some answer choices. There we go. Okay, now we're going to open a new section. Section 1.8, we're going to be looking at mathematical induction. Now, mathematical induction is a proof system. It's actually a very highly regulated or highly prescribed way of proving certain types of theorems. Now, you need to have a domain of the natural numbers when you're working with mathematical induction. You can't work with negatives or fractions. You need to follow the steps very, very carefully. It's highly structured, and we'll look at first the steps, and then we'll look at some examples. Some are in the book, and some are not in the book. The first step is to check the statement for the first element of the domain. Now, that's always n equals 1 unless the problem statement tells you otherwise. I have one of those where the problem statement tells you otherwise, so you can see one. So that's your first step. This is a very important step. Then you assume that the statement is true for some specific domain element k. And lastly, you prove it for n equals k plus 1, the next element in the sequence. Now this part right here, this is called the induction hypothesis. It's an incredibly important step, and I will be emphasizing it as we go along. And this is where you do all your work. You prove it for the next sequence element, k plus 1. Suppose we want to prove this sentence. Here's our sentence. The sum of n cubes is n times n minus 1 divided by 2 quantity squared. Well, first off, let's get it into math. Here we go. Let's get it into math. Write the claim out. The sum of n cubes is 1 cubed plus 2 cubed plus 3 cubed plus n cubed equals n times n plus 1 squared over 2, no, sorry, n times n plus 1 over 2 quantity squared. Now, nothing here is specified for n, so we want to start with n equals 1. If there were, it would be something like n greater than 3 or n greater than or equal to 4. It would be written right up there with the original claim in the sentence. So nothing was claimed, so we'll start with n equals 1. 1 cubed equals 1 times 2 divide by 2 squared. The 2's cancel. 1 squared is 1. That's right. Look, 1 cubed is 1 equals 1. Perfect. Now, just because I'm teaching this, I want to do it for some extra. I'm going to do it for n equals 2, 3, and 4. This is not part of the induction proof. If I have n equals 2, let's look at how we would look at this. This would be 1 cubed plus 2 cubed is 1 plus 8 equals 9. And on the other side, this is 2 times 3 divide by 2 squared, and your 2's cancel, and you get 9. For n equals 3, you would have 1 cubed plus 2 cubed plus 3 cubed, and that equals 36. And then on the other side, you would have 3 times 4 divide by 2 quantity squared. 2 goes into 4 2 times. That's 6 squared equals 36. So this is really working. And if we try it for 4, I would have 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, and that equals 100. And then I would have 4 times 5 divide by 2 squared equals, that's 20 divided by 2, 10 squared equals 100. So you can see that this is just working along. And in the proof, instead of doing these, we just jump ahead to a non-specific k. And we rewrite it 1 cubed plus 2 cubed plus 3 cubed plus n is now k, so this would be 1 cubed plus 2 cubed plus 3 cubed plus k cubed equals k times k plus 1 divide by 2 squared. And we assume this is true, and this is called the induction hypothesis. Right there. Now we've assumed it's true for k, so let's go here. Now we need to prove it for the next natural number, k plus 1. We need to prove it, and there's some work in that. Okay, so now my right-hand side was k times k plus 1 squared. Oh no, the squared goes on the outside. K plus 1. There we go. Divide by 2 squared. So this is from the induction step. Okay, so I'm going to have 1 cubed plus 2 cubed plus 3 cubed plus on up to k cubed, and then I'm going to have k plus 1 cubed And that's going to equal, now let's write this out very carefully. K is now K plus 1 times K is K plus 1 from the formula, divide by 2, quantity squared. So that's K plus 1 times K plus 2 divide by 2 squared. This is what I've got to show. I've got to show that working with the left-hand side over here, I can get this right-hand side. So the crux of an induction proof is the algebra we're going to look at right now. Now notice I boxed off the right-hand side, and I'm going to work with what's over here on the left-hand side. Now by hypothesis, I know what this is. All the way up to k cubed, that's going to be k times k plus 1 over 2 squared plus, and I think I want to get a common denominator because I'm old and I've done this a million times. So now, see, this was over 4, now this is over 4. And I'm going to very carefully write this as k squared times k plus 1 squared plus 4 times k plus 1 cubed all over the common denominator of 4. And then I want to note something for you. I want you to notice, see here, k plus 1 squared, 3 equals 2 plus 1. This is k plus 1 squared times k plus 1. So let me write it that way. This is k squared times k plus 1 squared plus 4 times k plus 1 times k plus 1 squared. And then I'm going to factor out the common factor k plus 1 squared. And I'm going to hold it right here. K plus 1 squared times k plus 4 times k plus 1. That's everything that's left. Okay, divide by 4. Just checking to make sure I've got it all written down right. So this is k plus 1 squared plus, now I'm going to distribute the 4. No, I didn't have it written right. This is k squared. K squared. There we go. K plus 1 squared times k squared plus 4k plus 4. All of that over 4. Now notice k squared plus 4k plus 4 factors. So this is k plus 1 squared over k plus 2 quantity squared over 4. And then I can write this as k plus 1 times k plus 2 all over 2 squared. And that's exactly what I need. I have proved that the left-hand side of the next term in the sequence equals what you would get if you put in k plus 1 on the right. So that's an induction proof. So see, there's some real algebra in it. Let's look down here. See, this is an induction proof. So let's review. The basic idea is that you show it works for the first natural number in the domain, and then you assume it works for a number k, and then you show that it works for the next number in the sequence, k plus 1. So then it works for all natural numbers. Now this is called the induction hypothesis. Okay, let's keep going with this. Here are the steps. Write the claim if you need to, and show it for the first n. That's step 1. Assume it for the first k numbers, that's the induction hypothesis, and then show it works for the next number in the domain and sequence, k plus 1. Let's look at another example. This one's not from the book. It is in fact by an author called Cohen. Here's our claim, and it's all nicely written out, and I want you to notice, see, look, the first element in my domain is 6, n greater than or equal to 6. This is an example that shows you where you're not starting at n equals 1. So write the claim. Well, it's already written out. Show it for the first n. 2 to the 6 is greater than 6 plus 1 squared equals 42. Yeah, well, 2 to the 6th is 64. That's greater than 49. I think I had my squareds in my brain. 7 squared is 49. Check. All right, the next step is the induction hypothesis. 2 to the k is greater than k plus 1 squared. Okay, now remember this is with k greater than or equal to 6. Now let's do the work. We have to write it out for the next number, k plus 1. So I had 2 to the k is greater than k plus 1 squared. That's my induction hypothesis. So this will be 2 to the k plus 1 is greater than k plus 1 from the formula squared. Okay. Now let me show you a little something. 2 to the k plus 1, that's going to be 2 times 2 to the k, same base and multiply as add the exponents, is greater than k plus 2 squared. That's what I'm trying to show. So let's go back to our induction hypothesis. 2 to the k is greater than k plus 1 squared. Now I'm going to multiply both sides by 2. And notice I've got 2 to the k plus 1 is greater than 2 times k plus 1 squared. Now, that isn't this yet, but let's work with it. Let's work with the right-hand side. This equals 2 times k squared plus 2k plus 1. That's equal. And if I distribute the 2, that's 2k squared plus 4k plus 2. Okay, we're working kind of carefully here. All right. Now I'm going to separate these k's. I'm going to reassociate. I'm going to take one of the k's and say k squared plus 4k, and then I'm going to stick in the other k over here, k squared plus 2. Now here's a little fact. I know that k is greater than or equal to 6, so k squared plus 2 at a minimum is 36 plus 2 is 38. So I know that k squared plus 2 is greater than 4. It's way more than 4 in some cases. So now I'm going to substitute here. I'm going to replace this by the letter 4, and instead of using equal signs now, I'm going to say greater than, so k squared plus 4k plus k squared plus 2 is greater than k squared plus 4k plus 4. Strictly greater. So now I've got 2 to the k plus 1 is greater than k plus 2 squared, which is what this is. This is a perfect square now. That's why I picked 4, so it would be a perfect square. And that's exactly what I want. So that's a fairly tough induction proof because it's an inequality. Let's now have Popper 2, question 3. All right, here are some steps from an induction proof. This is a real proof, by the way. There, I've got them all written down. Which one of these steps is the induction hypothesis? Which step? Is step 1 the induction hypothesis? Is step 2 the induction hypothesis? Step 3, step 4, or none of these? There we go. Okay. Here's another example. This is from the book. It's problem 1G, page 34. I'm going to take it further than the book did. For each positive integer n, 4 is a factor of 5 to the n minus 1. Okay, well, I'm going to write the claim in math talk. I'm going to say 5 to the n minus 1 equals 4 times x. 4 is a factor. That's what that means. I don't have to specify what x is, but I know that if I factored it to primes, 4 would be one of the factors. That's what this says. So I'm going to show it for n equals 1. 5 to the 1 minus 1 equals 4 times x. And in this case, see, x equals 1. So that's true. 5 to the 1 minus 1 is 4 equals 4 times x. So, yep, all right. Now, what's my induction hypothesis? Five to the k minus 1 equals 4 times some number. Now, I'm not going to call it x. I'm going to say times y. And then I have to show that 5 to the k plus 1 minus 1 equals 4 times some other number entirely. But 4, if you factored it to primes, 4 is a factor. Now, how am I going to tackle this? Well, I'm going to be kind of clever about it. I'm going to rewrite both of these terms. 5 to the k plus 1. Now, we should know this by now. See, that's 5 times 5 to the k. Now, here's a clever thing I'm going to do with 1. 1 is 5 minus 4. So this is going to be 5 times 5 to the k minus 5 plus 4. Okay, because I distributed the minus sign. And then I'm going to write this. Let's see, I'm going to group these two. And I'm going to say this is 5 times 5 to the k minus 1 plus 4. And then I'm going to substitute. I know what 5 to the k minus 1 is. It's 4 times y. So I'm going to substitute. This is 5 times 4y plus 4. And then I'm going to factor out the common factor of 4. This is 4 times 5y plus 1. And there's my z. So yeah, 5 to the k plus 1 is 4 times some z, and the z in particular is 5y plus 1. Perfect. So that's proved. Now let's look at Papero 2, question 4. I have a claim 2 cubed plus 4 cubed plus 6 cubed plus 2n, even numbers cubed. When you add them up, a finite sequence, when you add them up, you get 2n squared times n plus 1. So on this side, see, I've got a finite sequence and I'm adding it up, and it's finite because it ends. And there's the formula for the addition. Now, I've checked it for 1. I've done the induction hypothesis and accepted it. Now it's time to show it for k plus 1. Which of the following equations would I use? I'm going to show it for k plus 1. Am I going to use A or B? Here we go. All right, now let's get to our new section and next to the last section, 1.9, counting tools and how they apply. First off, let's start off with a discussion of the shortest routes that can be taken from point to point on a grid. We're only going to follow the grid lines. We're never going to go across a grid, no diagonals. The grid starts with one square and then grows by adding squares on the right, over here, and on the bottom. The grid grows in n squared for the number of squares in the grid, 1 squared, 2 squared, 3 squared. But the shortest routes from vertex to vertex in the grid, or node to node in the grid, grow in a totally different special pattern called Pascal's triangle. Now, here there's one route from A to B and one route from A to D, but two routes from A to C. Now if I grow my grid, notice I went from 1 squared to 2 squared, four blocks. Here I've got my 1, and my 2. Here's another 1 from D to E and 1 from D to I. However, there's 3 routes from A to H and 3 routes from A to F and 6 routes from A to G. They're length 4. See, 1, 2, 3, 4, 1, 2, 3, 4, like that. And still 2 routes from A to C. So we're tracing C. Here's 1, 2, 3 to H, 1, 2, 3 to H, 1, 2, 3 to H. So there's 3 routes of length 3. So let's start organizing the information based on the grid. We will always have one from a perimeter point to the next perimeter point on the top and the left side. We'll get different numbers from A to the points on the right side and bottom as the grid grows. Let's do next up a growth period to 9, 3 squared, which will be 16 points, 2 to the 4 points. So here we go. How many shortest routes from A to M? No diagonals allowed, but still from A to M, 20. That's a lot. So from A to L, 10. Now, these roots are symmetric about the diagonal from A to N, so if it's 10 to L, then it's 10 to N. Let's see, how about A to K and A to 0? It turns out there's 4 and 4. So there's our new numbers. It's still, let's see, A to G is 4 and A to C is 2. So you might have been thinking 2, 4, 6, but look, 2, 4, 20. There's a pattern to it. We'll just have to work out the pattern. Let's put the numbers themselves in a grid. Here we go. I've got a table here. So this would be like A and B and E and J. A to B is 1. And then here's D and C, 2 roots from A to C, F and K and I and H, 3 roots from A to H, and 6 roots from A to G. And if we're filling in now, if we go a little bit bigger, here's P, O, N, and M. If I expanded this, the next point on the diagonal would be 70. So on the diagonal, it's growing 2 to 6 to 20 to 70, and then to 352. And the numbers are symmetric about the diagonal. If there's a 35 here, then there's a 35 here. And let's see, I've got a 15 here, 15 to 21, 15 to 21, see, 35 to 56, 35 to 56, 70 to 132, let's see, 126, 126. Notice I'm just filling these in now. So I'm filling them in using symmetry. Now, how did I know what numbers to put on the table since I didn't draw the array? Well, it's a secret, but I'll show you the secret. Look. Four plus 6 equals 10. 20 plus 15 equals 35. 4 plus 1 equals 5. If you go to the box right there and you pick up these numbers, 1 and 5 equals 6. You add them. So here, see, 126 plus 126 is 352. So you add on the left and top and then fill in the box. See, so here's another one. 21 plus 35 is 56. It's a pattern, but it's not real obvious. Believe it or not, though, several cultures have figured this out with various applications over time. They use different stories and different representations to get the numbers, but they basically had the pattern down. We are going to focus our work on a system worked out by Blaise Pascal, a French mathematician in the 17th century. He had no computers, and he worked this out. Meanwhile, though, let's have Popper 2, question 5. Looking back to the box on page 17 in the notes, which of the following statements is true. So here are my statements. There are 6 roots from A to G. The number of roots from A to L is the same as the number of roots from A to N. A. Both are true. B. Not A. 1 is true and 2 is false. C. Not that. 1 is false and 2 is true. Or D. Neither of them is true. Okay. Now, Dr. Pascal used a different orientation on the numbers. He started with a 1 in the row, in the top row, which we'll designate as the 0th row. And then in row 2, he picked up these 2 1s. And then in row 3, he picked up 1, 2, 1. And then he picked up 1, 3, 3, 1. And then he wrote out 1, 4, 6, 4, 1. And you can see he is actually working with diagonals from the box, and he put them into rows. So here we go. Here's Pascal's triangle. The 0th row is a 1, and then we have 1, 1, and then we have 1, 2, 1, and then 1, 3, 3, 1. And to get the next entries, notice he makes the adding then, instead of adding on a diagonal, you add this way. 1, what goes here is 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So to get the next row, 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then you put your 1. So let's look. See? 1, 5, 10, 10, 5, 1. Yep, that's exactly right. That's the next row. So he's done a different format, but it's the same information. Let's note the adding pattern and put in 2 more rows. Here's a 1, a 6, a 15, a 20, a 15, a 6, and a 1, and a 1, and a 7, and a 21, and a 35, and a 35, and a 21, and a 7, and a 1. So there's the next rows. And if we look up here, you can see if we have a 1 here, we would get a 7, a 21, a 35, a 35, a 21. And let's see, there'd be a 1 here, so we get a 7 here. So yeah, that's exactly what's going on. Now, Pascal's situation was not our situation. What he was working with was polynomial multiplication of a binomial x plus y, and he focused only on the coefficients of x, y, and their multiples. Let's look at this. See, where we were working with a box and we were adding grid to the grid, Pascal said x plus y to the 0 power is 1. So that's my first row, 1. X plus y to the 1 power is 1x and 1y. X plus y squared is x squared plus 2xy plus y squared. So that's 1x squared plus 2xy plus 1y squared. X plus y cubed, if you multiply x squared plus 2xy plus y squared times x plus y, you get x cubed plus 3x squared y plus 3xy squared plus y cubed. 1, 3, 3, 1. So you're working strictly with the coefficients 1, 3, 3, 1. So how about, what are the coefficients for x plus y to the 4th? Well, 1, add these two, 4, add these two, 6, add those two, and a 1. Let's look at the pattern. So this will be 1x to the 4th, y to the 0, plus 4x cubed y to the 1, plus 6x squared y squared. Do you see the pattern I'm putting on the exponents too? 4x to the 1, y cubed, plus 1x to the 0, y to the 4th. So that's where he got his information from. What's the 5th row? 1, 5, 10, 10, 5, 1. How does it fit? Well, you would just pick up a coefficient here. This one is 5 times x to the 4th, y to the 1. This one is x to the 5th, y to the 0, and they're added. So we'll do the 6th row and then pick out a few more. So this will be 1, 6, 15. Add these two is 20, 15, 6, and 1. Let's look at this one. Y to the 0, y to the 1, y squared, y cubed. This one is going to be 20x cubed, y cubed, plus 15x squared, y to the 4th. That's where this one goes, and so on. Now, look at all the patterns. My goodness, there are a lot of patterns going on here. So let's step away from Pascal's triangle for a moment and review some counting methods to combine items, and then we'll ramp up the math a little bit. If you have a restaurant menu with 5 appetizers, 7 entrees, 3 choices of bread, and 4 desserts, how many meals can you make of these choices? Well, you multiply them all and you can make 420 meals. And you can, if you have enough paper, make a tree diagram. You would first have 1, 2, 3, 4, 5 entrees, and then 1, 2, 3, 4, 5, 6, 7, and then you would put 3 on each of those, and then you would put 4 on each of those. and you would end up with 420 tick marks. See? Like that. You'd have to do that to all of them. So it would be complicated. This is, however, called the fundamental counting principle, and in the book on page 40 is a nicely written proof of this principle by induction. So this is why we went through induction, so you could see a proof of the fundamental counting principle. I want you to read the proof very carefully and make sure you can see each step of the induction process being written up in that proof. Now, the next two ways of counting things are combinations and permutations. Here's the formulas. In a combination, order does not matter, while in a permutation, order does matter. So if we have the permutation of n things taken r at a time, it's n factorial over n minus r factorial. So suppose n equals 6 and r equals 2. Then the permutation of 6 things taken 2 at a time is 6 factorial divided by 4 factorial. So that would be 6 times 5 times 4 factorial divided by 4 factorial. These cancel and you get 30. Now the combination of n things taken r at a time has an additional divisor down here, r squared. So it's n pr divided by r squared. So let's look at that. 6 things taken 2 at a time for a combination. That's going to be 6 factorial over 2 factorial, 4 factorial. So that's going to be 6 times 5 times 4 factorial over 2 factorial divided by 4 factorial. This will cancel. 2 goes into 6 3 times, leaving us with 15. So look, a combination is a permutation with an extra item divided. So there are fewer combinations than there are permutations for the same n and r. Let's look at popper question 6. Okay, the combination of n things taken r at a time compared to the permutation of n things taken r at a time, you need to fill in the blank. There we go. Now going a little further with the math on this, there's some alternate notations for combinations that I want to introduce you to if you haven't already seen it. The combination of n things taken r at a time can be written with large parentheses instead of the c, and the n is on top and the r is on the bottom, and it's the same formula. So both of these symbols, NCR and parentheses NR, are read the combination of n things taken r at a time. So let's calculate the combination of 7 things taken 4 at a time with no calculator. There I've got it worked out. So that's 7 factorial over 4 factorial, 3 factorial. So that's 7 times 6 times 5 times 4 factorial. And the 4 factorials cancel. And 3 factorial is 6. So that's going to be 35. Now, let's go back to Pascal's triangle. The entries in our first table and in Pascal's triangle are all combinations. First off, let's know that 0 factorial equals 1. So the combination of n things taken none at a time is 1, and the combination of n things taken n at a time is 1. Let's have question 7 in our popper. Fill in the blank. The combination of 5 things taken 3 at a time is 1, 3, C is 5, D is 7, E is 10. So let's look at our new notation in Pascal's triangle. The first row, the combination of 0 things taken 0 at a time is 1. That is the entry. And then 1, 0, 1, 1 is 1 and 1. And then 2, 0, 2, 1, 2, 2, 1, 2, 1. 3, 0, 3, 1, 3, 2, 3, 3, 1, 3, 3, 1. And then I want to point out something to you. This is x plus y cubed using only the coefficients. But the interesting thing about this is, if this is x cubed y to the 0, this 0 is the 0 that's on the y. And this is 3x squared y to the 1. See that 1? And this is 3x, let's see, x, y squared. There's the squared. And this is x to the 0 y cubed. And there's the exponent on the y. So there's some utility to the combination notation. It gives you some hints to the pattern. So if we check out, let's see, the second combination in row 3. Row 3 is right here. Here's the second combination. So this would be 2 factorial over 1 factorial, 1 factorial. Yep, that is going to be 2. What will the combination pattern be for row 4? Okay, now I know it's going to be 1, 4, 6, 4, 1, but let's write it out as combinations. So this will be 4 and a 0 on the y, 4 and a 1 on the y, 4 and a 2 on the y, 4 and a 3 on the y, 4 and a 4. Let's check this one. This should be a 6. Okay. This will be 4 factorial over 2 factorial, 2 factorial. So that's going to be 4 times 3 times 2 factorial. And that cancels, leaving me with that. And that goes into that 2 times. And there's my 6. That's exactly right. So these things are accurate. It works right out. Now there's one more thing to check, and that is the adding secret from earlier. You get the entry you're working on by adding on the diagonal in the box, or adding by the 2 above. See, like that. Adding those two gives me my new coefficient. How do we say this in combinations? Well, we say it right here. N plus 1 in the next row, the rth entry is from row n, r minus 1 and r. So here's my n plus 1 r right here. And here's my n r minus 1. And here's my n r. And they're added. That's right here. So that's how we say it. Let's check this with n equals 3 and r equals 2. Let's see. So here we go. If n equals 3, then n plus 1 is 4, and r is 2, equals 3, 1, plus 3, 2. So let's see. 0, 1, 2. The 6 right here in row 4, this is 0, 1, and 2. Remember how we count. This is 4, 0, 4, 1, 4, 2, right here, is from the third row, 0, 1, plus the 2. That's exactly right. That sets us up exactly right. Now, the justification steps are worked out in the book, and they're very interesting. If you get stuck threading through it, make an appointment with me or come by my conference hours to discuss how they proved it. Let's look at Popper 02, question 8. If I give you this, what is n? Is n 8, 7, or 5? Now for our last section, the binomial theorem. In this section, we will concentrate on Pascal's application, multiples of x plus y. So we have x plus y to the 0, the combination of 0 things taken 0 at a time, and that equals 1. That's just x plus y to the 0. Now, 1, 0x and 0, 1y, 1x and 1y. 2, 0x squared plus 2, 1xy plus 2, 2y squared. That's exactly right. Those are how they work out when you expand the formula here. Expanding means that we multiplied it out. Pascal's triangle has entries of, these are the coefficients of the expanded binomial. Let's look at x plus y cubed. Row 3 of Pascal's triangle is 1, 3, 3, 1. So here's 1x cubed y to the 0, 3x squared y to the 1. Notice that the exponents here add up to 3. 2 plus 1, 3x to the 1 y squared, 1 plus 2, 1 x to the 0 y cubed. So here is the expanded x plus y cubed. I've put in some extra exponents so you can see the exponent pattern in x and y. See, here's 3, 0, xy, 2, 1, xy, xy, xy. So not only the coefficients have patterns, the exponents that are suppressed in the presentation of the triangle have patterns. So let's write this out in combination form. 3, 0 is 1, x cubed y to the 0, 3, 1, x squared y to the 1, 3, 2, and 3, 3. So now let's skip to row 5 and let's look at these coefficients. This coefficient right here, if I'm counting over 0, 1, 2, this is going to be 5, 2, like that. And then it's going to be x cubed y squared. I knew the y squared from here, and I knew this had to be a 3 because these exponents have to add back to 5. See how that works? And so here I would pick this one. 0, 1, 2, 3, 4. The power is 5. The place is 4. This will be x to the 1, y to the 4th. The 4 goes right here. And I know this has to be 1 because these exponents have to add back to 5. So there's all kinds of patterns in this. Now, in the book, on page 49, there's an abstract and idealized listing for x plus y to the n. Any power that's a natural number. This generalized expansion is called the binomial theorem, and each coefficient nr is called a binomial coefficient. The n is for the nth row and the power on x plus y to the n, and the r is for the term index starting with 0 when you count over on the y. So if you have 5, 2, x to the 3, y squared, you know it's from x plus y to the 5th, and it's the third term over because you start your count with 0. 0, 1, 2, term number 3. So, and then a reminder, note how the exponents add to 5 are n. So here's Pop Row 2 question 9. Okay, the combination of 11 things taken 7 at a time times x to the 4th, y to the 7 is which term when you count from the left to the right in the expansion of x plus y to the 11th. Is it the 11th, the 7th, the 4th, the 8th, or the 3rd term? Okay, now I'm going to put the binomial theorem here in our notes. X plus y to the n is the summation, that's what this symbol means, summation adding up all the terms from r equals 0 to n, using the combination of n things taken r at a time times x to the n minus r times y to the r. So let's look at this now and write it all the way out for n equals 7 and r equals 4. So this would be x plus y to the 7th is what I'm doing. And I would start off with 7, 0, x to the 7 minus 0, y to the 0, and I would add a bunch of terms, and I want to get over to 7, 4, which would be the fifth term, x to the 7 minus 4 cubed, y to the fourth. And then I would keep on going till I got all the way out to 7, 7, x to the 0, y to the 7. So this is the one I want to focus on. So that would be 7 factorial over 4 factorial, 3 factorial. So that's 7 times 6 times 5 times 4 factorial. And 3 factorial is 6. So that's 7 times 5. So this will be 35x cubed y to the fourth. Perfect. Now, this section in the book closes with no surprises, an induction proof of the binomial theorem. I want you to read it. You don't have to memorize it. I'll never ask you for it on a test, but read it and find the steps. There's the basis step, S1 is true. There's the induction step, assume S sub k is true, and then show S sub k plus 1 is true by using substitution and good algebra. Here's our last popper. Show the combination of n things taken r at a time, x to the n minus r, y to the r, for n equals 10 and r equals 5. Okay, that wraps it up for this video. I will see you in the next video.